after a long time, I think. So I hope you are going through the assignment or take-home exam which I have given with DC circuits and all. So has anybody completed that? You have completed it. Okay. Who else? Only one person. So did you find any problems? Any easy to solve, or is it difficult? Is it easy? Is it? Do you have the thing? Yeah. So maybe then you can assume some value. I think it's required. So how much you want to assume? 5 amperes? One more?
We get one equation with two variables without knowing the value of R or without R.
See, the total current is also there. No? So I1 plus I2 is 2.25. So two equations, you know.
Then we have three variables. I1, I2 and R.
So another equation is
The KVL for the loop.
yeah. So the KVL for this loop, or this voltage equal to this voltage.
We only get I1, I2 and R, three variables in that equation. And in the other equation there are two variables, I1 and I2.
We'll see. Maybe after this, we'll see. Just give me 2 more minutes. We'll start. Put down. Okay. Yeah, I think it's working. So you can see a sine wave here. Slightly out of focus. So, but anyway, for the time being, we are not worried about this. Let's focus on the board. 1 second. We just. Okay, so I'll connect this later. All are small chalk pieces. Okay, good morning. Let's start today's lecture. Last class we thought we'll work on RLC circuits. So, but we could only finish only up to R. So, today we'll also see R, L and C and then RLC circuits in AC. So, let me write the name as RLC circuits. So, R is resistance, L is inductance and C is capacitance. These are three basic elements in circuits, and then we'll see how we solve a network which has all these values. Before we go into details, I want to talk about what is called as a J operator. So, you already know how to represent an AC quantity. So, AC quantity can be represented in the form of a phasor, which can be represented in the rectangular form, polar form and so on. Okay. So, let us take an example. Let us say you have current is equal to 10 sin omega t plus 30 degrees. Okay. So, some current is given like this. So, it is a sine wave. What is the value of omega is unknown. It is not required now because we are not worried about multiple values of omega. It's for all it's the same value. Now, how do you represent this in the polar form? I simply write I equal to 10 angle 30 degrees. Okay. Strictly speaking, it should be 10 by root 2. So anyway, why to confuse? I'll put a root 2 here. So this whole thing is the maximum value of current, and when you convert to polar form, it will become 10 and angle 30. Okay. So here the omega information is not shown because it's not required. For the entire circuit, we consider omega is same. So now you convert it into rectangular form. So what it will be? So it will be 30. It will be 10 cos 30. Cos is your horizontal component or x-axis component or the real component, and then plus 10 sin 30. Okay, so here you can put I. Okay, or you can see I is the imaginary number, square root of minus 1. So I is, or I can also call it as J. Okay, so because in electrical circuits I is used for current, so it will unnecessarily create confusion with current and all. So it's just a notation we use J in the electrical circuits. Okay. So here I'll put J. So so then it becomes, what is 10 cos 30? Cos 30 is 0.5, is it? So it is 5 and then plus J 8.66. Is that correct? Is it reverse? Okay. So where is the duster? Yeah, it's reverse. Sin 60 is 0.5. Huh? Yeah. So what is this? Plus J5. Is that correct? Sure? Okay. So now, so I'll put capital I just to. So now I want to talk about this J operator. So what happens is, let's say I multiply J with this. Okay. So if I take any quantity, multiply with J, what will happen? It will become, the real will become imaginary, imaginary will become real in that sense. So J 8.66 and then J into J is minus 1 because J itself is square root of minus 1. So it will become minus 5. Okay. So this was on vertical axis. Now it become horizontal axis with negative sign and all these things. Okay. So if you see, this is multiplied by J. So after multiplying by J, you are getting like this. Okay. So if I draw the figure, let's say this is my it's called phasor plane, and this is the real axis and this is the imaginary axis. So in this axis, if I draw the original I, so 8.66 and 5, or I can actually draw a length 10 units with angle of 30 degrees. Okay. So automatically this will have x-axis component of, let me mark it with different color. It will have x-axis component of 8.66 and then this one will be 5. So to represent that it is in vertical direction, I will use J5, this one. So the addition of these two is this one. Okay. Now what happened because of multiplication of J? So this 8.66, because of attachment of J, it will, from this axis it will go to this axis. Okay. So it will become like this. So this is now 8.66. Okay, so this one rotated by 90 degrees. Similarly, this one rotated by 90 degrees, and also you can notice minus sign. Because with minus sign, it is in the minus x-axis direction. So this is minus 5. So as a result, what is the now this total value? So this is something like this. Okay. So what is this angle between this and this? It will be 90 degrees. Okay. So what is the J operator doing? So if you multiply by J, then any phasor will be rotated by 90 degrees. Okay. So this is rotated by 90, this is rotated, any value will be rotated by 90 degrees. Okay. In fact, what is the polar form of J? See, J equal to 0 plus J into 1, isn't it? Just I am writing it in a more different form. The real part is 0 and then imaginary part is 1. Okay. So if you convert this into polar, what will you get? You will get 1 angle 90 degrees. So it's a phasor of unit 1 at the angle of 90 degrees. Okay. And when you multiply anything with this, the magnitude remains same. The angle adds by 90 degrees. So that J is a rotation by 90 degrees. That is required. Just remember that we will use that idea later on. Okay, that's about J operator. So what happens if I multiply J once again? So this is multiplied by J. So again multiply by J. 2 times I multiply by J. What happens? So J into J is minus, so it will become minus 8.66, and then minus 5 will become minus J5. Okay. So rotate by 90 degrees, again rotate by 90 degrees, rotation by 180 degrees. Okay. So this is the original one. So rotate by 90 degrees you are getting here, rotate by 90 degrees, it will be exactly opposite. So this will be exactly opposite to this. This is totally 180 degrees. Okay. So you can also see, so this minus 5 will become minus J5. So you can see here, it will be downwards, and this plus 8.66 will become minus, plus J 8.66 will become minus 8.66. So I think you get the picture now. Okay, that's about J operator. Next, before going forward, we'll see what is the behavior of inductor. Okay, so inductor. So just like resistance is represented by R, usually the inductor is represented by letter L. L is a value of inductance. What is it? We'll see. What is inductor? We discussed this last time. So there is this kind of coil, and then let's say I connect a voltmeter. Okay, I connect a voltmeter. Okay, so the current is 0, I equal to 0. When the current is 0, the voltage is also 0. It's not reading any voltage. So I'm saying current is 0 in steady state. It's open circuited, so voltage is also 0. Okay. Now my question is, I connect a current source here. Okay, let's connect a current source which is like, let's say, 2 amperes, and then I close this circuit. Okay. So I am asking the question, what is the value of the voltage? 0. Why 0? Okay, so one answer I got is the voltmeter is equal to 0 volts. Okay. The justification why voltage is 0 is that, by the way, this is a correct answer, but not 100% correct answer. So if I take time axis, this is time, okay, and then this is t equal to 0, okay, and the current is, see there, I'll put a switch here to make it more clear. So at t equal to 0, I close the switch. Before that, the switch is open. So how is the current? It is like this. So this is current. Okay. Now, what is the voltage of an inductor? So the voltage of inductor is nothing but proportional to rate of change of current. Okay, this is how it behaves. Now you can ask, why the voltage is proportional to rate of change of current? Okay, that has something to do with the physics or physical design of this coil. Whenever there is a current, there is a magnetic flux, and then the flux will try to, there is some kind of something called Lenz's law and all these things. So the flux will try to oppose the rate of change of current and all these things. So, and to oppose that, it induces a voltage in reverse direction and so on. But for our discussion, I am saying the voltage is proportional to rate of change of current. Okay. So what is the rate of change of current here? The current is constant 2 amperes, not changing. So the voltage will be 0. So the voltage will be, I'll use this color. So, but at this point, the rate of change of current is very high. Okay, so there will be a very spike in the voltage, and then the voltage will come down, and then it will be 0, something like this. Okay. So strictly speaking, the voltage is 0, but then the current not at the t equal to 0, at the time there will be a high voltage, and then it will be 0. What is the constant of proportionality? So that is the value is L. Okay. So the constant of proportionality value is L. So this L depends on, what kind of, how much is the length, how many number of turns you are winding, and then what is the area of cross section of your this one, and then what is the material that is there inside that. So it depends on the physical properties of this, okay, which we will not go into right now. So now the interesting thing, what happens, if I give a alternating current. So it's a current source, but it's an alternating current source. So now in the place of I have to put some I maximum sine omega t and all these things. But instead of doing that, normal case will not have a current is, normal case current is unknown, voltage is known. Okay. So I'll, instead of a current source, I'll use a voltage source. So V equal to Vm sine omega t. Okay. So some maximum value, some frequency, and some voltage I am applying here. Okay. So what is this voltmeter reading? So it's obvious, whatever it's just, see this actually the voltage is connected to the supply only. So whatever you are supplying, that voltmeter reads that only. Okay. So here the known quantity is voltage, unknown quantity is current. So what you have to do is you put an ammeter to find the current. Okay. So let's find what is a current. Okay. So this relation still holds good, but the problem is V is known and I is unknown. Okay. So what you do in this, you can integrate it and find out what is I. Okay. So how do you find what is I? So I equal to, so see on this side I already know what is the value. So V maximum sine omega t. So this one is already known. Okay. So I am asking the question, if I apply a sine voltage to inductor, what is the current? So what is I? So this L will go that side. So Vm divided by L. Okay. And then integration. So this constant I have taken outside. Okay. Sine omega t. Okay, with dt. Okay. So what is integration of this? Integration of sine, is it plus cos or minus cos? I always confuse that. So minus cos omega t. In fact, that's what I was just looking at before starting the class. Is it plus or minus? Okay. And the omega will come in the denominator, I think. What else? So now this minus cos, I can write it. See, I want to go back to sine. Okay, how to go back to sine? So sine 90 minus omega t. Is that correct? Or omega t minus 90? Okay. So you just verify it. This is just a trigonometry thing. So I am not immediately proving or anything. Just minus cos theta is nothing but sine theta minus 90. Now this one will be your I maximum or I. So this quantity I can consider it as a the maximum value of current. Okay, so and this quantity is this one. Okay. So what is this minus 90 degrees? So minus 90 degrees means you are multiplying by minus j, because we just saw j operator. If you multiply by j, it is plus 90 degrees. If you multiply by minus j, minus 90 degrees. Okay. So what I'll do, I want to get j omega L here. So multiply by minus j Vm by omega L, then I can write it sin omega t. This is correct. Okay. Because instead of writing minus 90, I am multiplying by minus j, that is a j operator. Okay. Now from numerator I can bring it to denominator, because it's like multiply by j on both sides. Actually, see, minus j is 1 by j, okay, something like this, because minus of j square is plus 1. Okay, see, j square is minus 1, so minus of j square is 1, and then minus j is 1 by j. Okay, so it's just, so minus j is actually 1 by j. Okay, so I'll write it Vm by j omega L is equal to, into sin omega t is equal to my I. Okay. So finally we solved the problem. The objective was, given the voltage, what is the current? So now I got the current like this. Okay. Now compare with the resistance. So since this anyway is recorded, so I'll rub it. Compare with the resistance. See, if it was a simple, this is voltage and then the resistance. So what is your I? V maximum by R sin omega t. This was my current in a simple resistance circuit. Okay. So in the RL circuit, what? Sorry, in the inductance circuit, what is I? V maximum by j into omega L into sin omega t. So what is exactly happening is, the role of resistance is played by this quantity j into omega L. So whatever role of resistance is been played, that is taken by this one. Okay. So now what you can do, I can replace it something like Vm by XL sin omega t. Okay, where XL is, it is called reactance. It is not called resistance, because resistance implies some losses are there and all. So this is the reactance. So where XL value is nothing but j omega L. So finally this is the point that I wanted to say. Okay. We will see a lot of examples of how to use this. But anytime you see a network, see, this is like Ohm's law now. Okay, I equal to V by R, or I equal to V by reactance, or in general terms, I is equal to V by impedance. So that's about the inductor. Okay. Now, if you want to draw phasor diagram, so it will be something like this. So if this is my V, this arrow represents my V, so this arrow represents I. So 90 degrees lagging. Okay. How do you know it is lagging? Because if you go clockwise, this is coming first, and after that this is coming. So current is lagging by 90 degrees. So how much is the magnitude of this I depends on the value of the L and the value of the omega. Okay. So if you increase omega, that means you increase the frequency, then what happens? If you increase omega, X will increase, and therefore I will decrease. Okay. So this is an inductor. And if I keep on increasing the frequency of the supply, the inductor will offer more and more reactance or impedance. I'm not using the word resistance, but it's opposition, and that will make the current less and less. Okay, so the higher the frequency, the higher is the opposition offered by the inductor. Okay. Now, very quickly, now it is easy now. Let's do RL circuit. Okay. It's a circuit which is having these two elements. Okay. So there is a resistance and then there is a inductance. Okay. Something like this. So this is Vm sin omega t, some value R, some value L. Okay. So this is given. So you can actually use Ohm's law. So let's denote this voltage as VR, voltage across resistance. This voltage let us denote as VL, voltage across inductance. VR plus VL will be nothing but VS, supply voltage. Okay, so VS equal to VR plus VL. Okay. So this is just a Kirchhoff's voltage law. So in a closed loop, the voltage will be 0. Okay, so that means Vs minus Vr minus VL equal to 0. So why these two are minus? Because here I am increasing the voltage and then voltage drop Vr, voltage drop VL, and then 0 volts. Okay. Now I can simply replace. So this L is nothing but the property of this device or element. What is the reactance offered by it? Minus j omega L. Okay, or I can simply write it j omega L plus j omega L. Sorry, that's what I was wondering. So sometime back I just said XL is equal to j omega L, but just forget this j. Just say XL equal to omega L. It's a matter of notation. So XL is actually omega L, so I can keep j when I write it. It's just a notation, so nothing important there. So now I can apply Ohm's law. See, the question is same. How much is the current? Okay. By simple Ohm's law, I can write I equal to V by the impedance, total impedance. So that is R plus j omega L. Okay. So here I can write it I RMS is nothing but V RMS by this one, or I maximum is nothing but V maximum by this one. Okay. So I don't have to do any other calculation in this sense. Okay. So now the V itself is a phasor. So I'll use this line to represent a phasor. But then later on we'll not even do that because it's understood. Just for now, and I is also a phasor. So like this. So now imagine R is 0, purely inductance circuit. Okay. If R value is 0, then this purely inductive is there. Then what is the phase difference between V and I? So it will be 90 degrees because R is 0. J represents rotation by 90 degrees. So divide by J represents backwards rotation by 90 degrees. So I will be lagging V by 90 degrees. Okay. On the other word, if you imagine L is 0, in that case, so if L is 0, then I and V both are in phase. Okay. So this is voltage and then this is I. So this is the case where L equal to 0 and R equal to some value. Okay. So another case is voltage and then current. Okay. So here voltage is still same, current is 90 degrees lagging. So if both have some values, then you will get some combination like this. Okay, some angle phi. Okay, so this is V and this is I. So this is a case for a RL circuit. The voltage will be leading and the current will be lagging. So depending on the values that you choose, the amount of how much angle it is lagging will change. What if omega is 0? So what is the meaning of omega equal to 0? It's nothing but DC. Okay. So when you apply a DC, then this, assuming that it's a pure inductance, there is no resistance in this, then it is just like a DC circuit. So I equal to V by R. Because omega is 0, whatever value of L is there, doesn't matter, it will be there. Okay, so now let's talk about C. So main point that you take over is, from this is nothing but XL is omega L. Okay, so L value will be given. So by the way, units also let me say, L is inductance, and then inductance is measured in henries, and then the henries, usually it is represented, unit is H. Normally you have millihenries, microhenries, and so on. Okay, 1 Henry is quite large value. So normally our devices will have millihenries or microhenries. So what is the unit of XL? So the unit of XL is ohms, okay, because it is like under this. So this is ohms, this is ohms, okay, but this ohms is real ohms, this ohms is imaginary ohms. So there is actually no resistance. We are imagining that some resistance is there. So that's why this one, and then this is volts and amperes. So to get volts and amperes, we need ohms in the denominator. So that way. Okay. So let's talk about capacitor. So the problem is same. For the time being, resistance is 0. So this is the symbol for capacitance, and the C is the value. So the value of C is again depends on the physical design of your capacitance. How much is the length of your capacitor plates, how much is the distance between these capacitor plates, and what kind of material you are using inside between these two capacitor plates, and so on, this thing. So that we will not go into right now. So the question we are asking is same question. If I apply this voltage, how much current will flow through this circuit? Okay. So what is the behavior of this element C? So will it oppose the, for what does it oppose? Does it oppose the variations in current, or does it oppose variations in voltages? So inductor opposes variation in current, because inductance, what it is trying to do, when some current is going in inductor, it is setting up a magnetic field, and that magnetic field does not want to change very fast. So how to keep the magnetic field fixed and not change very fast is by keeping the current same. So all the time inductor is trying to oppose any variations in the current. Okay. So here in capacitor, what happens? The capacitor is charging, and when it charges, it develops some voltage. Okay. So it wants to keep that whatever charge inside it as a constant. Okay. So whenever you try to change the charge, it will try to oppose it, or for that some current needs to come. So it's a reverse relation. So the current, see, whenever voltage across it changes, current has to be there. Okay. So current is nothing but C dV by dt. Okay. So rate of change of voltage is nothing but current. Okay. So in order to increase the voltage, you need positive current. In order to decrease the voltage, you need negative current. In other words, we are saying in order to charge, you need to send the current. In order to discharge, you need to take the current. Okay. So this thing is charging, discharging. So the moment you send some current into it, it charges, voltage increases. Okay. Okay. So C is like that way, it is positive. You are getting this, right? dV by dt is I. Okay. So what if I forget about this circuit for a time being? What if there is a capacitor and then I connect a current source, constant current source of 1 ampere, and then this C. Okay. I am just sending just current like this. Okay. So what happens to this? So continuously current is flowing like this. So this is time t equal to 0. At t equal to 0, I close the switch and then sending 1 ampere current. Okay, what happens? So the current is like this. What happens to the voltage? This is I. So I have given I am asking what is V. See, 1 ampere current is flowing, it will charge the capacitor, voltage will increase. And then again it will increase, again it will increase. So voltage keeps on increasing. Okay? So it is like this. So it keeps on increasing. Okay? So at one point what will happen? The voltage becomes like, voltage is like 10 volts, 100 volts, 1000 volts, 10,000 volts and 1 million volts and all. After a point, the voltage becomes so high that there is some kind of a spark and then it totally burns or something like that. So, so the same thing is with the inductor. Okay? What do you do for inductor? You take an inductor and then put a battery like this, 3 volts or 5 volts or whatever battery. Then what is the current? It's a constant voltage applied to. So basically I am asking what is the integration of constant? Multiply by T. So it's a like this. So in this case, for this one, this is my V and this is my I. So current will start increasing. So 1 ampere, 10 amperes, 100 amperes, 1000 amperes, and after some time it will burn. So don't connect a voltage source directly to inductor, and don't connect I mean to say DC voltage source. AC voltage source you can connect. Why can you connect AC voltage source? Because there is a positive cycle, current will increase. There is a negative cycle, current will decrease. Okay. Similarly, here also don't connect a current source to a capacitor. It will overcharge and burn. But then you can connect a AC current source because it will charge and discharge and all these things. Okay. This was some side discussion. So these things, we can ask in the interviews or you can ask in the exam or something like that. What happens if you connect a current source to capacitor? Okay, come back to this. So what is I? So you can just solve this. So I equal to C d by dt of Vm sin omega t. So C Vm d by dt of sine. So what is differentiation of sine? So we'll get plus cos. So cos omega t. And then what is cos? Sine, omega also is there. So I'll write it omega c. Sin omega t plus 90. Okay, so this is the effect of converting cos to sine. Again, it's just a what you call trigonometry thing. So now to remove that plus 90, I'll put j omega c Vm sin omega t. Okay, so this is I. So now I want it in the form of Ohm's law. Okay, so what I'll do, this Vm I'll keep it like this only, and then I'll put divided by 1 by j omega c. like this. So this quantity is called, see what I'll do is, this J I will bring it to numerator here. So I'll get a minus, and then this J I'll take it out. Okay. So J into minus 1 by J omega C. Okay. So this quantity inside this brackets is XC. Okay. I can write XC equal to minus 1 by omega C. So don't worry too much about this sign. When you are writing it in the circuit, it should be correct finally. So what is the units of this? Again, the units is ohms. And what is the unit of C? It's farads. Okay. C is measured in farads, and the symbol is F. Okay. Normally we use microfarads. Okay. What is microfarad? 10 power minus 6 farad. We also use picofarads also. 10 power minus 9 farads also. 1 farad is very large amount. So what about the vector diagram or phasor diagram? So if this is V, so you can notice the current is some quantity multiplied 90 degrees plus. Okay, so it will be like this. Okay, so V into I is, or V into J is I. So it will just, and then the length will be different based on the value of C. Now we can talk RC. What happens if there is RC? If I introduce R in this, then what? So this voltage is VR, this voltage is VC. Okay. Voltage of resistance, voltage of capacitance. VR plus VC is Vs. Okay. Now question again, what is current? Okay. So you can write I equal to, so V divided by, so I RMS, let's call it, here also V RMS, divided by R. Okay. See, you can write plus, so we had that minus, right? So minus J into 1 by omega C, something like this. So we will solve a problem, so don't worry about how it works out and all. We'll just solve an example problem. So in this case again, if R is 0, then minus J will become plus J and I will be 90 degrees leading. And if C is, so C is 0 means I think C should be infinity in this case, or what? Yeah, so the Farad's point, it is actually, if not having capacitor means it's an infinite kind of thing. So anyway, if this total quantity is 0, then V and I are in phase. So I can write it, this is voltage and this is current. Okay. In the case of only pure resistance, in the case of only pure inductance, this is current. In the case of only pure resistance, sorry, this I said I for only pure capacitance, I for resistance, and the I will be like this for if you have a both R and C. Okay. So and this angle will depend on the relative values of R and C. Okay. And what if you have all the three together? So if you have all the three together, there is an inductor also here. Okay. So then up to here is VC and this is VL. Okay. So three voltages, VR plus VL plus VC. Okay. So this is L. So how do you represent? This is R itself. This is okay minus J by 1 by omega L. So, or I'll just write it minus J XC, and then this is plus J XL. Okay. So because these two are J's, I can add them. Both of them are in imaginary. So depending on which one is more, so if the inductance value is more, then it overall behaves like a inductance circuit, and if the capacitance value is more, it overall behaves like a capacitance circuit. So we'll try to see some examples on this one. Okay, let's just take a 1 minute break. We'll try to set up the circuit and see if it is coming. Values. Okay. Before we look at the circuit itself, okay, so try to see what is there on the screen here. I'll make it full screen. So, so here you can see some sine wave. So this is our supply wave. Okay. So input voltage. So how much is the value? So you can see down here. I know it is not clear for you all to see it. I'll just tell what it is. This is 20 volts, right? So that is peak to peak value. Yeah. So you can see here 5 volts per division. So one division is 5 volts. Okay. So this is, if you take this one as 0, 5, 10, 15, 20. So because there are 4 lines, so it is 20 volts from peak to peak. Okay. So if it is 20 volts from peak to peak, what is the from 0 to peak? 10 volts. So if it is 0 to peak is 10 volts, what is the RMS value? 10 divided by root 2. How much is 10 by root 2? No. 7.07. Okay. So, yeah.
10 ohms. This is 100 ohms and this is 22 ohms.
Okay. So we'll try with this. You can come here. Okay. So maybe we'll just I will just want to write something here. So the circuit we'll try is something like this. I have ten sine omega t. Okay, so that's the voltage I have. Then I have So I'll put the resistance. So this is 10 kilo ohms, okay, and this is 100 millihenries. Okay, so this is my circuit. So I want to give what is my frequency also. Frequency is 1000 hertz. Okay, so F is 1000. So let's do some quick calculations. So what is XL? XL is nothing but omega L. Okay. So what is omega? 2 into pi into F into frequency is 1000 into 100 into 10 power minus 3. Okay, because this is millihenries. Okay. So what is the value of all of this? So this 1000 and this one will get cancelled. Okay. 2 into pi is 6.28 into 100 is 628. 628 ohms. Okay. Let me just verify. So what is the frequency? Yeah, so we'll make the frequency 10 kilohertz. Okay. See, because this is 10 kilo ohms, I want something, maybe we'll replace that also. So if I make the frequency 10,000, then this will become like this. One extra zero will come. Okay. I'm putting one extra zero here. Okay. So this I can write it 6.28 kilo ohms. Okay, 6.28 kilo ohms. Okay. Now let's calculate what is current. So you are following this. So what is my total impedance? Impedance is denoted by Z. This is R plus J XL. Okay. So R is 10 kilo ohms plus J XL is how much? 6.28 kilo ohms. So total is in kilo ohms. I'll write it here. Okay. So this is my impedance. Okay. Because we are going to divide it, you better to convert impedance into polar form. Okay. So how to convert this impedance into polar form? So can someone convert it and tell me? So this is a complex number, convert it into polar form. So I have some place here, I'll write, see, I is equal to V by Z. This is just a Ohm's law for AC circuits. Okay. So what is V? I'll not write everything, I'll just write the RMS value. Okay. Or I'll write the peak value. So I max is V max by Z max. Or you can also use for RMS. I'm just writing peak value so easy to refer. Okay. So 10 divided by, what is my Z? 10 plus J 6.28. Okay. How much is this? 10 square plus 6.28 square under square root. That will be the magnitude. How much is that? 11 point? Are you sure? $11.81. Anybody wants to confirm that? 10 square plus 6.28 square under square root. So how do you convert a real number into polar form? You must already know it. We have done it more than once. So how much? Or you want me to try it? $11 point? Okay. So let's call it 11.8. And what is the angle? 32 degrees. Let's call it 32 degrees. So now if I divide 10 by 11.8, how much is it? 10 divided by 11.8. 0.84. Okay. This is 0.84 milliamperes. Remember, because this was in kilo ohms. So this is 0.84 milliamperes or 840 microamperes, whatever. Okay. And what is the angle for current? It will be minus 32 degrees. Okay. Because the angle when it here the angle is 0, so it goes up. Division means minus, so it will become minus 32. So this is my current value. Okay. So if the 10 is the peak value, then 0.84 is also the peak value, 0 to peak. Okay, like that. Or if you are using here RMS, here also you will get RMS. So don't confuse. So we will verify now. So I connect a 100 millihenry resistance circuit. I connect a 10 kilo ohms resistance, and I measure the voltage and current, and then we will verify. Okay. But there is one small problem. The CRO, that what you are seeing on the screen, has two inputs, two channels it is called, but both of them measure only voltage. You cannot directly measure current and see the waveform. Okay. So, but because the current, whatever current is proportional to this one, so what I will do is one like channel 2, I will write it CH2. Channel 2 will measure this voltage across only R, and channel 1 will measure the complete voltage, CH1. Okay, like this. So now I want to compare channel 1 and channel 2. So in that case, what is VR? So VR is I into R. Okay, so I is 0.84 into this one. So it will become 8.4 because 10 kilo. So the kilo and milli will cancel. 0.84 will become 8.4. Okay, so 8.4 at angle of minus 32 degrees. Okay, so you will see one channel 1 is at peak to peak 10 at an angle of 0 degrees, and the channel 2 will be 8.4 volts at angle of minus 32 degrees. That's what we have to verify now. Okay, so let's see how much we can verify it. We'll just totally focus on the screen here. Okay, let's look at the circuit first. So we are connected. Okay, so on the right side you can see this red and you can see the black wire on the right side. So that is actually the supply. Okay, so the supply is coming like this. Then this element is the inductance, whose value is, this is the inductance whose value is 100 millihenries. So if you actually open it, this one, if you break it with a stone or something, inside you will find there is a coil, and then it is number of turns it is wound and all this thing. And the value is 100 millihenries. And this one is 10 kilo ohms resistance. So these two are connected in series, and then it is there like that. So one work is you have to see channel 1, which is the voltage of this one. So for seeing that, you can see there are two measuring this thing. So that is connected to channel 1. Where is the connection for channel 2, which we are doing now? Only the R. Yeah, it's okay. So after connecting this, so let's look at the, I don't know whether it is working correctly or not. So let's see. Maybe I'll move a little forward. So here you can see two. Maybe we can adjust the what you call these divisions and things like that. So the yellow colored one is actually the supply voltage, channel 1, and the green colored one is actually the voltage across the resistance. Okay. So is the values coming correctly? So why don't you just move the yellow one away and then we'll only focus on the green one, and then we'll just touch this here. Just slightly move it down. Okay. So what is the peak to peak? Okay. So from here it is 1 division, 2 division, 3 division, slightly more than 3. Okay. So each division is 5 volts. That's how we set it up. So how much is this? 15 plus something. So let's consider it as 16. Okay. So the total peak to peak is 16. Okay. So what is 0 to peak? 8. Okay. We are supposed to get 8.4, but we are getting 8 volts. But it's okay. It's a slight variation. We just calculated that, so we got 8.4. So this is this one. Now the next thing to verify is the phase difference. Are we getting 32 degrees phase difference? Okay. We still have time. So how do you measure phase difference? We have to see how much time between the 0 of first one to the 0 of the second one, okay, or the peak value of the first one to the peak value of the second one. We have to measure the time. Okay. So what is the time axis? Okay. So you see that there is one small vertical line moving like this. So which is aligned with the peak value of the channel 1, that is the supply voltage. There is another line. It's just a way to measure it, and then you can see some numbers here. She will be telling it. So how much is the time we are getting? The time difference between this and this, the peak value of the first one to the peak value of the second one. So by the way, which one is leading, which one is lagging? You can tell it directly by seeing this. So the supply voltage is leading and the resistance voltage is lagging, because which is achieving the peak value first? The peak value achieved by this one first. It's nothing to do with the magnitude, but the time at which. And what is the time difference between these two? Okay, so from the measurement we are getting 10.4 microseconds. So maybe slightly you can move it to the board. We'll see. So I'll keep the 32. I'll keep this one. VR should be 8.4 volts minus 32 degrees. Okay. So maybe I'll use this place. So my frequency is 10,000 hertz. Okay. If the frequency is 10,000 hertz, what is the time period? 1 by 10,000 seconds. Okay. So this is how much? So I want in microseconds. So to 100 microseconds. So because there are 4 zeros, I'll take 2 zeros and 6 zeros are in micro. So 100 microseconds is my time period. That means if I draw the waveform like this, from this point to this point, it is 100 microseconds. If it is 0 microsecond, then it is 100 microseconds. Okay. So 1 microsecond. See, 100 microseconds represent 360 degrees in angle. Okay. So 1 microsecond represents 0.36 degrees. Is that correct? Sorry, 3.6 degrees. Okay. Now, because we measured from the device, how much is the time difference between the peak of these two values? How much is the time difference? 10 microseconds. Okay. So that means 36 degrees. Okay. So we were expecting minus 32 degrees, so it is more or less correct. Okay. So like this. Okay. So like this, what I hope you have followed what we have done. We created a simple RL circuit and tried to measure the current in that, and we verified the current is correct and also the this one is correct. The phase difference is also correct. Okay. So we have tried on some, 1 or 2 lectures back, we have seen how to draw the waveform, how to find the phase difference and all this. So let's do quickly one more this one, because we also have capacitor also with us. Okay. So this capacitor is, let me write down now. So I'll extend this circuit. Okay. So here I will introduce a capacitor. Okay. And the value is strangely 4.7 nanofarad. Okay. 4.7 nanofarad. So what is nano? 9. Okay. Nano is 9. Okay. So let's calculate what is XC. So first you do 1 by omega c. How much is 1 by omega c? 1 divided by 2 into pi into f. F is 10,000. And c is how much? 4.7 into 10 power minus 9. Okay. So this is how you calculate this is omega and this is c. So 1 by omega c is your xc. Okay. So how much is this? So this 4 zeros, here it will become minus 5. Okay. So this will be 1, 2, 3, 4, 5 divided by 2 pi into 4.7. Okay. Can you calculate this? This is 5 zeros. How much? 3386. So we'll neglect that. 3386 ohms. Okay. Or I can write it 3.38 or 3.386 kilo ohms. Okay. Now, in order to represent it is XC, I'll put minus J. Okay. So just minus J indicates it's a XC. Because when I substitute it in the Ohm's law, what will happen? I equal to V by XC. The minus J will multiply with I, and then will it become plus? Yeah, because J is in the denominator, it will go to the minus J will go to the other side, it will become plus. Okay, we'll see that. So I'll just keep this value and then I'll remove this whole thing. So what is XL? We just calculated XL. What is XL? Just now we calculated. See, 100 millihenries, 6.28 kilo ohms. Okay, this is plus J. Now, the overall effect, is it inductance or capacitance? So the overall effect is inductance, because inductance value is more. So it still behaves like a inductive circuit. Okay. Now, what is the net reactance? X. Net reactance. It is plus J. How much is that? 2.9. 2.906. So I'll call it 2.9 kilo ohms. Okay, this is net reactance. So what is the net impedance? So my resistance is still same, 10 kilo ohms. Okay, K I will not write it now. Plus J, 2.9 kilo ohms. Okay, are you following? This is my net resistance. Okay. Now what is in polar form, what is the impedance? 10 square plus 2.9 square under root. How much is that? 10 square. I am convert this into polar form. So I am actually solving upwards. So after I get Z, I will calculate I. I equal to V by Z. So that is 10 divided by whatever Z is there. So that will have some angle with negative sign and some magnitude. Okay, so what is that? 10.4, only that much? Okay. Are you sure it is 10.4? Okay, and what is the angle? How much? Okay, 16 degrees. Okay. So this is plus angle because here J is plus. Okay. But then because now J will be dividing here 10.4 16 degrees. So it will become, what is 10 divided by 10.4? 0.96, and then the angle will be minus 16 degrees. Okay. Now if I still do this same channel to measure voltage across this one, so it will, I am expecting my VR, voltage of resistance, will be 9.6 volts, because the kilo ohms and this is milliamperes will cancel out with each other, and then 10 into 9.6 is 9.6 volts, and what will be the angle? Minus 16 degrees. Okay. So minus 16 degrees is how many microseconds? We saw 1 microsecond is 3.6 degrees. Okay. So how many microseconds will be 16 degrees? How much? No. 4 point? So 4.4 microseconds. Okay. So, or approximately 4.5 microseconds, assuming we can see. So now I'll add this capacitor into the circuit, and then we'll see whether we are getting these values or not. Okay. Don't do it now itself. Yeah. Now action. So you notice here, this is the input supply coming like this, and then this is the capacitor, then this is the inductor series, and this is the resistance in series, and it is going back to the supply. So that's the whole RLC circuit. And one channel I am measuring the total supply voltage, another channel I am measuring only the resistance voltage. Okay. If I switch over to the another camera, so okay, so here we are trying to measure the time difference. So since it is difficult for to directly see and do it, the way it is done is there will be some guidelines. You can just adjust it, and then it will show how much is the difference. So how much is the difference? So 4.8. Okay. So 4.8 microseconds we are getting, which is almost within the limit. Okay. Let's also verify the peak. This one. How much is the magnitude? So check with the connections. Okay. So you see it is slightly larger now. So this is 0, 5, 10, 15, and the above one is 20. So maybe it is like 18, slightly less than 20. So 18 by 2 is 9. So we are expecting 9.6 actually. So it is more or less similar. And if you just align these two, so this is how the actual waveforms look. One is the waveform of the supply voltage, and other is the waveform only of the resistance. So can we try quickly one more thing? What is the voltage only across, so we still have 5 minutes. So what is the voltage only across L? So can you tell what is the voltage only across L? VL. What is VL? So now what I'll do is, I think we cannot connect it. Okay. Can you just go to the board again? So now my question is, what is VL? Just look at the circuit. So this is 10 angle 0 degrees. This is my V supply. Okay. And this current I just calculated, it is 0.96 angle minus 16 degrees. Okay. This also I calculated. Okay. Now remember that this 10 was peak to 0 to peak value. Therefore, this 0.96 is also 0 to peak value. Otherwise, normally we use RMS value. Don't get confused. Now, what is VL? Voltage of L is nothing but I into XL. Okay, I into XL. So, what is I? 0.96 minus 16 degrees. And what is XL? 6.28, and the angle is 90 degrees. Remember, it was JXL, so I have to put 90 degrees angle. Okay. So what is the total now? 0.96 into 6.28. How much is that? How much? 6.03. So I'll write it 6 volts. And 90 minus 16 degrees. How much is that? 74 degrees plus 74 degrees. Okay. So this is my VL, voltage of inductor. Okay. So I'll just write it. So you will notice that the voltage of inductor will be leading the voltage of our supply voltage. Okay. And leading by 74 degrees. So how many microseconds? So 1 microsecond is 3.6 degrees. Okay. So 74 degrees is how many microseconds? 20? Approximately 20 microseconds, because 72 and 3.6 does that. So let's see if we are getting those values. And the magnitude is 6 volts. Okay. Okay. So the circuit we have to connect is something like this. You can see this will move here. So this is C and then R and then L, and then this will be channel 2 and this will be channel 1. We have only 2 minutes. Not updating. Okay, so let's go to this, and this is the last thing that we are seeing. So now immediately you see the yellow line is the supply, this one, and then leading. Why it is leading? Because it is achieving the peak value before the supply voltage achieves the peak value. Let's measure the amplitude. So we'll align it with one of the, this one. Okay, so this is 0, 5, 10 and slightly more than 10, so maybe 12. Okay. So peak to peak is 12, therefore 0 to peak is 6, which confirms the voltage of inductance. And what about the phase difference? So here what we have to measure is from the peak of this to the peak of this, how much is the time difference, which we are expecting to come somewhere around 20 micro. Yeah, so almost 20 microseconds. So like this. So you will get an opportunity sometime to visit the lab and all. You can actually do this on yourself, and then you can check it sometime later. Okay. So I hope you have understood what we have done. So maybe in the last 1 minute, quickly I'll tell one more point, just on the board. So imagine a circuit is given like this. This is a capacitor. Then I am drawing backwards. So something like this. This is A and this is B. Okay. So you have to find what is the impedance between A and B given all the values. So what will you do? Represent this as Z1, represent this as Z2, and represent this as Z3. Okay. Then you can parallel all of them. So 1 by Z1, 1 by Z2, 1 by Z3, and then add them, and then again make it 1 by. Then this whole thing will become one impedance. Okay. So that one impedance, let's call it, I will not put any symbol inside this. Let's call it, so depending on, let's say Z3, depending on the J value is positive, then it is inductance. The J value is negative, then it is capacitance. Then these two are in series, like Z3, this Z and this Z are all in series. So you can add them. Add the real component, add the imaginary component, you will get the total impedance. Then parallel with this. So 1 by that, 1 by that. So like that you can find the total impedance. So the point I am making is whatever DC circuit analysis you have learned also applies to AC circuit analysis. Only thing is DC circuit real numbers, AC circuit is complex number. You need to know how to calculate with complex numbers. Okay. So with that we'll stop here. We'll see the next class on October 13th, okay, Monday. So I will also make a couple of announcements based on regarding your assignment, and also I am trying to prepare one assignment on AC also. That also I'll give it to you. Okay. We'll communicate by email on that.